Hello, Mrs. Bricky here. This is Math 1050 section 4.6. We are modeling with exponential and logarithmic functions in this section. There's 3 topics, but I have one topic from 4.5 that I like to include in this, so 4 topics total. The first topic is finding the initial amount and rate of change given an exponential function. So we're going to compare these functions to the equation y equals a times 1 plus r to the power t. On your formula sheet, remember that it includes the letter n, but for this course, our n value is always equal to 1. N is the number of compoundings, so we just have a 1 for that value. So if n is equal to 1, this is what the formula looks like. So in this formula, a is the initial value, r is the rate of change in decimal form, and then t would be time. If r is positive, the function represents growth. If r is negative, it's decay. So we're going to be comparing to that equation. So we have a problem here. A study is done on the number of bacteria cells in a petri dish. Suppose the population size p of t after t hours is given by this exponential function right here. Our first job is to find the initial population size. Well, the initial value in this type of function is a, so you can see that that's 2600. If you ever forget that, remember that initial just means t equals 0. So if you sub in 0, this is 2600 times by 1.03 to the 0 power, but 1.03 to the 0 power is just 1. So this is 2600 times 1, which is 2600. So if you remember that it's that initial number right there, great. If not, plug in 0 for t. Okay, the next part has to do with figuring out if it's growth or decay and the percent change here. So we're going to look at the base for that. The base of this function is 1.03. And if you compare it to the function above, that's 1 plus r. The base is 1 plus r. So you can see that r in this case would have to be 0.03. Now that is in a decimal form, and in order to report our answer as percent, we need to convert that into percent form. So in percentage form, this would be 3%. So our answer here would be that 3%. It has the percent symbol for you, so you just have to type in the 3. And then to answer if it's growth or decay, this is a positive number. So that means this is a growth situation. Here's another example. A can of soda is placed inside a cooler. As the soda cools, its temperature, C in degrees Celsius after t minutes, is given by this exponential function. So again, we want to find the initial temperature. So remember that that number in front gives you the initial, in this case, temperature, 27 degrees Celsius. If you forget that, you will get that answer by subbing in 0. Initial means at t equals 0. So again, anything to the 0 power is 1, so we get the answer 27. Okay, so now we're going to compare the base. So the base of this type of exponential function is 1 plus the rate, and here we have that that's 0.96. So 1 plus the rate is 0.96. If you have a hard time doing that in your head, or if you just like to be careful, we are just subtracting 1 to figure out what r is, and we get negative 0.04. Now that is in decimal form, and we need to report our answer in percentage form. So this would be negative 4%. Now to report this into ALEKS, the negative tells you that it's decay, So we'll mark decay here. And then you would type in your percentage into the next box, in this case 4%. Do not type the negative in here. The negative is covered by this decay box. So you would just put the value 4%. All right, next topic. Finding the rate or time in a word problem on continuous exponential growth or decay. So the key word here is continuous. And because it's continuous, we know that it is base E. So on your formula sheet, you have this little, I guess in yellow, this little paragraph, exponential growth and decay model, y is equal to y naught e to the kt, where y naught represents the initial value of y. If that k is positive, it represents exponential growth. If k is negative, it's exponential decay. So our first problem here says, suppose that the number of bacteria in a population increases according to a continuous exponential growth model. We've got a sample of 2,900 bacteria. So that is telling me y naught, the initial value, 2,900. 2,900 bacteria are selected from the population, and they reach the size of 2,991 in 1.5 hours. So when t is equal to 1.5, our y value is 2,991. Our job here is to find the hourly growth parameter, and this is k. We need to write our answer as a percentage. All right, so what we're going to do is we're going to put these 3 given bits of information into our equation, and then we'll solve for k. So we have y first, so that's 2,991. It's equal to the initial value 2,900 e to the k times time, k times 1.5. So we need to solve for k. So the first thing we want to do to solve this is divide by this coefficient 2,900. And you could get a decimal here. I prefer to just leave it in fraction form. If you get a decimal, you could end up rounding at, after some number of decimal places, and that could give you a slightly off answer. So I would just leave it in fraction form. And I'm going to go ahead and put the 1.5 in front of the k, because I like to have numbers in front of variables. Okay, so we've got this equation, 2,991 over 2,900 is equal to e to the 1.5k. So we can rewrite this into log form, because right now it's an exponential equation. We can turn it into a logarithmic equation. It's going to be a natural log because it's base e. So this will be the natural log of 2,991 over 2,900 is equal to the power 1.5k. So maybe it looks like I didn't use the e, but remember it's a base e log, so it's a natural log. So the e did get used there. So we converted this exponential equation into a logarithmic equation, and our goal is to solve for k. We're really almost there. We just need to divide both sides by 1.5. I'm going to write it as like the fraction 1.5, just because I think it'll be easier to put it into the calculator. So I just divided both sides by 1.5. Okay, so we can put that into our calculator now to solve for k. Now this is exponential growth, so we should be expecting a positive number for k. So 1 over 1.5 times the natural log of 2,991 over 2,900. Whoops. And that should give us our k value. Now it wants us to report it in, move this over here. It wants us to report it as a percentage, and it wants us to round your percentage to the nearest hundredth. Well, in decimal form, this is 0.0205 0.020598. That is in decimal form. So to convert that into a percentage, we want to move that decimal 2 places, and then after that round to the nearest hundredth. So we would round to this spot. So we would report our final answer as 2.06%. Okay, let's try that same topic with a decay. Suppose that, oh, this is not decay, sorry. We'll do a decay in a minute. Suppose that $1,900 is invested at an interest rate of 3.25% per year, compounded continuously. So again, that word continuous is what tells us we're using this model with a base E. After how many years will the initial investment be doubled? Oftentimes the word doubled throws people for a loop. If this is our initial investment, doubling would mean $3,800. Just times that initial amount by 2. Okay, so the bits of information that it gives us is that our initial amount of money is $1,900. The Y value doubles at some unknown time. And that's kind of our goal, is to figure out T. But this time it tells us that rate. And again, this is in percentage form. We need it in decimal form. So that's going to be 0.0325 for K. We'll put these numbers into our equation. 3,800 is equal to initial amount E to the K times T. So we're going to solve for T. We would start by dividing by 1,900. And this one does divide nicely because it's doubled, 3,800. So that is just a 2. So you can write it that way if you want, or you can leave that fraction for a minute. So we've got an exponential equation, and we're going to rewrite it in log form. Because it's base E, it's going to be a natural log. So this will be the natural log of 2 is equal to that power, 0.0325t. And we just need to divide to get our answer. So the natural log of 2 divided by 0.0325 gives us t. In our calculator, if we type that in, rounding to the nearest hundredth gives us 21.33 years. Okay, next topic. The next topic is finding the time given an exponential function with base E that models a real-world situation. So we've got Frank putting a bottle of water inside the cooler. As the water cools, the temperature is given by this function, where T is the number of minutes since the bottle was placed in the cooler. He wants to drink the water when it reaches a temperature of 12 degrees Celsius. How many minutes should it be left in the cooler? So we're solving for T. So we want the temperature to be 12 degrees, so that is going to get subbed in for the temperature. So our equation looks like 12 is equal to 10 plus 8 e to the negative 0.025t. So we'll need to subtract the 10. And then we would need to divide by that 8 coefficient. So I'm going to reduce that fraction to 1/4. You could do a decimal as well if you like. Just if you have a decimal, make sure you don't round it. So now we have our exponential equation. We can convert that into log form. It's base e, so it's going to be a natural log. So the natural log of 1/4 is equal to negative 0.025t, and we just need to divide by that negative 0.025 to get our answer. Sometimes when I've already got something complicated happening, I'll just write it as 1/. So we can put that into our calculator to get our final answer. So 1/, negative 0.025 times the natural log of 1/4. And so we get 55.45177. It asks us to round to the nearest tenth. So we will report our answer as 55.5 minutes. Okay, last topic, but I am going to do 2 examples of this one. We are finding either the half-life or the doubling time. So we've got a massive radioactive substance following a continuous exponential decay model. So that tells us that we're using this exponential growth or decay model from our formula sheet. This has a decay rate parameter of 5% per day. Now that is decaying and it's in percent form. So if we write our K value, it's negative because of decay, and it's 0.05 in decimal form. Our goal is to find the half-life of the substance and round to the nearest hundredth and don't round any intermediate computations. So we are finding the half-life. So that is when y is equal to 1/2 of y naught. So if we sort of fill into our equation, we want 1/2 of the amount that it starts with, and we are solving for t. So we've got the ending amount, which is half of what we started with, is equal to the starting amount times e to the power kt. So if we divide both sides by y naught, the y naughts are gone. So we get 1/2 is equal to e to the negative 0.05t. We can rewrite that in log form, and it's base e, so it's going to be a natural log. So that's the natural log of 1/2 is equal to the power, which was negative 0.05t. And our last step is that we just need to divide by negative 0.05. So we get 1/, negative 0.05 times the natural log of 1/2 is equal to t. So in our calculator, negative 0.05 is our divisor, times by the natural log of, sometimes when I need to type in a 1/2, I'll just type a 0.5. Okay, so that gives us 13.86, and that was a 5% per day, so that gives us days. 13.86 days. It asks us to round to the nearest hundredth. So 13.86 would be our rounding. Okay, so that one is finished. That was half-life. So for this last example, really the last one, is going to be about doubling time. The amount of money invested in a certain account increases according to this function that it gives us. Y naught is the initial amount, y is the amount present at time t, and our goal is to figure out after how many years will the initial investment be doubled. Well, double means that y is equal to 2 times y naught. So we'll sub that in to our equation for y, 0.045t. So if we divide the y naught, it divides out on both sides. So we get 2 is equal to e to the 0.045t. We can rewrite that in log form. So this will be the natural log of 2 is equal to 0.045t. And we just have the one last step of dividing both sides by 0.045. And if we evaluate that in our calculator, we get, this said round to the nearest tenth. Make sure you're really watching your rounding statements because every problem could be different. So if we round this to the nearest tenth, that's going to be 15.4. And this is years. And that's it. We made it. So let me know if you have any questions or are having troubles with any of these topics. Thanks so much.